All right, good to go. All right, hello everyone. We'll just be waiting for 2 or 3 minutes just for people to join us. Thank you for joining. I hope everyone's doing well on this Thursday evening. Bear in mind that there is a bit of a delay between the live stream and the YouTube stream. And the way that we'll be communicating with you is through, if you want to type in any questions and communicate with us via the YouTube chat, and we're happy to take any questions and communicate that way. And maybe just to test that the communication is working, could you tell us what locations you're tuning in from? Comment on the YouTube channel what location you're tuning in from. That would be great, just so we can test that communication. Thanks for joining. Nice, you got Cambridge. Oh, we have Christina Rodriguez next door. Paris, Hertfordshire. Great. And maybe just so we have a feel of the general audience, if you're comfortable, maybe it would be great if you could type your age or the age of the youngest person who is with you. That would be useful for us, just so we have a feel of the audience that we're presenting to. Oh, we've got London, Canada, Cambridge, Surrey. Awesome. Yeah, so if you could comment, if you're comfortable, your age or the age of the youngest person who's watching with you, just so we get a feel of the general audience, if there are any younger members, so we can tailor the way that we speak. Thank you all for joining us today. I think we'll be starting in just a minute. All right, thank you. All right. We do have some youngsters, that's great. Always good to see young people. We have someone from Birmingham, great. All right, all right. All right, awesome. So I think we'll get started at 5 past. Hope you're all going to be enjoying this bank holiday weekend. And thank you all for joining us today on a Thursday evening. Right. All right. So just before we get started, a reminder for anyone who just joined, if you can comment the city you're tuning in from, and if you're comfortable, the age of the youngest person who's watching with you, just so we have a feel of the audience. So yeah, we're gonna get started then. So my name is Joseph, and this is my teammate Colin, and we're students at the University of Cambridge in chemical engineering and biotechnology. And today we're going to be talking to you about what we work with, which is related to energy and fuels of the future. And so just to get us started, I want to talk about energy. And I want to specifically ask, what do we need energy for in our daily lives? And if you can comment what we need energy for in the chat, that would be great. And I'll be reading out your answers. So think about, what do we need energy for generally in our lives around us? So I'll get us started with one example being that we need energy for lighting in our homes or our workplaces or outside on the street. Are there any other things which you think that we need energy for? We'll just wait for the answers. Don't be shy, feel free to comment. So one thing we need energy for is lighting. What other things do we need energy for? Well, yep. Thank you, John. Everything. Straight to the point. Anything else? To move, yep. To get around, exactly. To drive our cars, yep. For heating our homes, for example, or heating our offices. Another example is in construction, for example. For transportation, for heating our food or our water, indeed. And for driving planes, flying planes or driving trains. So we need energy for a lot of things around us. Agriculture, exactly. So we need energy to power our lives. And where does our energy generally come from? So most energy today comes from what we call fossil fuels. Does anyone know any examples of fossil fuels? If once again, comment what fossil fuels, examples of fossil fuels in the chat, and I'll get us started with one. So an obvious fossil fuel that we use is petrol. And if you can comment any other fossil fuels, give if you have examples of fossil fuels, please comment them. We'll just wait for the answers. Coal, oil, gas, yep. Atharva's got them all. Yeah, exactly. So yeah, propane. So another example of a fossil fuel is oil, which we can either take from on land or in the ocean. Another one is coal, which we, for example, burn in power stations to provide electricity. And lastly, gas or natural gas, which is what we use in gas hobs at home, or methane, exactly, Andrew. So these are all examples of fossil fuels which is where our energy comes from. And so I want to talk more about what exactly fossil fuels are made of. What are their building blocks? So we also call fossil fuels hydrocarbons. And this gives a hint as to what elements they're made from. So fossil fuels are made of hydrogen and of carbon. And here's the simplest example of a fossil fuel, which some have already mentioned, which is methane. And this fossil fuel is made of 1 carbon and 4 hydrogen atoms. And it also happens to be the gas which is in our gas hobs at home. And so looking at methane, and which is the simplest example of a hydrocarbon, when we use a hydrocarbon or when we burn a hydrocarbon, we release heat, we release carbon dioxide, and we release water or steam. And the problem with fossil fuels is that the carbon in them, when we burn it, releases carbon dioxide, which is released into our atmosphere, and it creates a layer above, it builds up in the layers above in our atmosphere. And the buildup of this carbon dioxide sort of acts like the glass of a greenhouse on a hot day. It traps the heat in, and it does this around our Earth. It traps heat in, and this causes increased temperatures, or what we call global warming or climate change. Melts the snow caps and results in rising sea levels and extreme weather conditions. And so the carbon dioxide, which we release from the carbon in fossil fuels, builds up in the atmosphere and causes climate change. So there's a lot of engineers and scientists that are trying to work to overcome this problem, which is to do with the carbon which is in fossil fuels, to try protect and save the environment. And so looking at our molecule of methane again, well, the problem is mainly with this atom of carbon, which we have here. And so one simple solution is just get rid of the carbon and use, for example, hydrogen, which is a possibility which many are discussing at the moment. And it does have some potential applications. But the main issue with hydrogen is that it's such a light and explosive fuel. So when you burn hydrogen, it releases heat, you get water, but the issue is that it's really explosive, and you need a huge volume to store the energy, because hydrogen is such a light gas in its natural form at room temperature. And we're going to demonstrate this to you in a second. We're going to show you some videos where we were blowing up some balloons of hydrogen just to show you how explosive they are. But in our group, we believe that, okay, originally we had hydrogen atoms that were attached to a carbon atom, and this allowed for higher energy density. So in our group, we believe that it's possible perhaps to switch the carbon for another atom like nitrogen. And this molecule here is called ammonia. So all we've done here is, rather than dangle the hydrogen off of a carbon atom, we're dangling off of an ammonia atom. And ammonia has a lot more energy, can store a lot more energy than hydrogen. In fact, the balloon which we blow up in the video I'm about to show you, the entire balloon of hydrogen, which I also have here, it's a big balloon, pink balloon. All the energy contained in that balloon of hydrogen can be stored in just a cup of liquid ammonia. And so ammonia can store more energy, and it can be made a liquid very easily, and so it's easier to store and to move around. So I'm going to show you the video now of Colin and I blowing up some hydrogen balloons, just to show you that all the energy contained in the balloon of hydrogen, which is like this big, could be stored in just this much ammonia. So I'm just going to share my screen and get to the video. All right. Full screen it. So yeah, just to show you that entire, actually I can show the video again especially for the younger audience members. Let me just get there. So yeah, just to reiterate, that entire balloon of hydrogen, all the energy contained in it could be stored in just a cup of liquid ammonia, which is why we really see ammonia to be a very potential fuel of the future, because of how much energy it can store in such a small volume. And it is effectively just swapping out that carbon atom, which is in hydrocarbons, for a nitrogen atom. So now I'll hand over to my colleague, Colin.
Okay, so let's talk a little bit more about ammonia. Can anybody tell me what ammonia is used for today? If you want to comment in the chat with your ideas about what we use ammonia for right now. I'll give you a hint. It's actually very important for our society, our daily lives, even if we don't see it very often. It's actually keeping all of us alive in a scary way. So just waiting for, yep, exactly, fertilizers. Yes, so ammonia right now is currently produced in the millions of metric tons per year, and it's primarily used as a fertilizer. But there's other applications for it as well. It's used in some cleaning solutions and aqueous solutions, and it's also used as a refrigerant in a number of applications, the most interesting of which being it's actually used on the space station to cool down the solar panels as a refrigeration technique. And actually, if you want to really get a feel for how pervasive ammonia is in our lives, you just have to look at a map of ammonia being transported around the globe. That's what this map shows here. You can see the red shows the very high concentrated areas of ammonia transport. And you can see it goes all over the world and there's a lot of it. So it's very important for our daily lives. In fact, approximately 50% of our food supply comes from fertilizers such as ammonia, among other complementary fertilizers, but that's just how important it is for our lives. So the question is, where do we get the energy to make the ammonia? Now, as Joseph was talking about, most of our energy today comes from fossil fuels such as methane, but you can also make ammonia in addition using methane. You can also use oil or coal or anything really, any sort of fossil fuel can make ammonia. Typically today it's made with natural gas with methane. And that's really unfortunate because that ends up meaning that ammonia, the production of ammonia accounts for approximately 1% to 2% of all global CO2 emissions, which is really unfortunate that this molecule that's keeping at least 50% of us alive is also causing 1% to 2% of global CO2 emissions. So, but our vision for ammonia going forward in the future as a fuel and as an energy storage medium is that we would get the components, which is hydrogen and nitrogen, from cleaner sources. So first, with regards to the hydrogen, you can actually get hydrogen straight from water. If you split water, you can just get hydrogen straight away and oxygen gas. And then as far as nitrogen is concerned, 80% of the atmosphere is nitrogen. So that solves that piece of the puzzle. And when you combine these two, of course, you can make ammonia using renewable energy such as solar panels or wind turbines. And it's for this reason, the fact that ammonia can store this energy from renewable energy in, as we showed, a very dense and liquid form, that we think it's the fuel going forward in the future, most likely. And the question is then, how do you get the energy from ammonia? So the way that you get the energy back from, there's a number of different ways. The way that we look at, particularly in the group, is decomposing the ammonia back into its components, as I said, hydrogen and nitrogen. And then you can take that hydrogen and then use it as a fuel. So you're using the ammonia as an intermediate storage mechanism in a more compact and economical form for that hydrogen. You decompose it back to the hydrogen, and then you can use the hydrogen to get energy from it. So then what do we do in the lab? So in the lab, and the reason why we're giving this presentation as two, together is because we work on the two different sides of ammonia. So what I do in the lab is that I make ammonia. So I take hydrogen and I take nitrogen and I combine them in a reactor to make ammonia. And Joseph does the exact opposite. He takes ammonia and breaks it back down. He decomposes it into its elements, into nitrogen gas and hydrogen gas, because then we can use the hydrogen gas to do useful things, as I was saying. And then because of this, the running joke in the lab is sort of that we're constantly in conflict, because I'm constantly making ammonia and he's constantly breaking it down. So there's this friendly conflict there between us. And so just in summary, we think that ammonia can serve as the fuel for the future because first, it doesn't have carbon in it. As Joseph was saying, the carbon is replaced with nitrogen. And secondly, as we showed by blowing up hydrogen, that it can store a lot of energy in a small amount of volume. And what we do in the lab is to find better ways to make ammonia and better ways to extract energy from it, in particular by breaking it back down into hydrogen, but there's also other ways to use ammonia for energy. And our work is done in the catalysis and process integration group in the chemical engineering and biotechnology department, led by Laura Torrente. This is our group there, all together in the lab back when we were able to do that. Thank you for your attention and happy to take any questions in the chat here.
So maybe before we go into questions, we can do a quick quiz for the younger members of the audience. So we just thought we would do a quick 4-question quiz just to make sure that sort of the fundamentals of what we're talking about have gotten through. So quiz 1, which of these is a fossil fuel? Water, coal, or air? So comment your answer for question 1, whether A, B, or C in the chat. So which of these is a fossil fuel, water, coal, or air? And question number 2, what are fossil fuels not made of? Oxygen, carbon, hydrogen. So one of these things fossil fuels are not made of. Hint, the fossil fuels are also called, we also call fossil fuels hydrocarbons. So maybe that can give you a hint as to what they're not made of. So comment your answer for question 2, whether A, B, or C. And question 3, what do you get when you burn a fossil fuel? So nitrogen, carbon dioxide, or hydrogen. So if you can comment your answer to that, 3A, B, or C, what do you get when you burn a fossil fuel? And then lastly, what is ammonia mostly used as today? A fuel, a detergent, or fertilizer? So comment 4A, B, or C. What is ammonia mostly used as today? A fuel, B, a detergent, C, a fertilizer. So I see we're getting a lot of answers coming through. That's awesome. So at this point, I guess I can go back through the questions and start giving the answers. So which of these is a fossil fuel? Well, coal is a fossil fuel. It's what we use to power our daily lives, not water and not air. So coal, we usually burn in power stations to provide electricity. So what are fossil fuels not made of? So they're not made of carbon. Fossil fuels are made of hydrogen and carbon, hence we call them hydrocarbons. And 3, what do you get when you burn a fossil fuel? Well, you mainly get carbon dioxide. You also get water as well, as we've discussed. And lastly, what is ammonia mostly used as today? As Colin spoke about a lot, it's mostly used as a fertilizer. And so hence there's a lot of infrastructure already there for it. It's already traded a lot. The infrastructure is present for its use as a fertilizer. Hence we also see its potential in being used as a fuel, since it's already a chemical which we know how to use and distribute. So yeah, that was the quiz, mainly for the younger members who have been watching. And we're happy to take any questions. So you can comment your questions in the chat, and then we'll open a Q&A. It can be about anything, about our daily lives as scientists. It can be about the ammonia, about the energy. So please ask away, and we'll be reading out your questions and answering them as best as we can. So thank you all for listening, and we hope you enjoyed the talk. And no matter how old you are, and no matter what your background is in, no matter where you are, which is something I guess, Colin, is just quite nice that it's online, is that people can join from anywhere basically. As we have Canada in the building. We're not in the building, but we have Canada on the on the live chat. Yeah, thank you all for joining us for this interactive session. The online format has been quite different, but it's nice to see people's engagement on the chat. So just waiting for the questions now. Thank you, John, for your question. Very interesting line of research, but shouldn't you be talking about an energy carrier rather than a fuel? So I would respond to that saying, as in yes, I guess an energy carrier or an energy vector are different ways of describing it. But we guess that the word fuel is a word which we chose because it's more relatable to people in their general lives in terms of fuel, petrol. But we do envisage that you could use ammonia, for example, in an ammonia power station. In that sense, it is sort of fueling the power station to provide energy. What would you say, Colin?
Yeah, I'd say we definitely also call it an energy carrier as well. That's one of the other terms we use for ammonia, and that's what it's ready to be used for very soon. With regards to hydrogen, everything is already set up there. Using it as a fuel, that's a little bit more in the future sort of sense, as far as if you're thinking in terms of like cars and things like that.
Indeed, yeah.
Because using the ammonia in a fuel sense is really the more challenging area of that. But we use it as both. Fuel is more of a futuristic sort of a thing. Right now, it's more of an energy carrier, as you said.
Indeed, yeah. And in this way, or an way of storing energy, for example, storing renewable energy between the summer and the winter months. So if we have a lot of solar energy in the summer and much more than we need, then we can use that extra energy, as Colin was describing back here, to make the ammonia out of clean sources like water and air. And in that sense, you've effectively used the ammonia to store that energy or carry the energy from the wind turbines and the solar panels. So yeah, thank you, John, for that question. So Andy's asked, what is the biggest issue which stands in the way of ammonia being the fuel of the future? Colin, do you want to give your opinion on this? I would say it's the electrolysis. I don't know, what you would say?
So we can talk about it from both sides of the coin, right? Because there's the using the ammonia and there's making the ammonia. When you're making the ammonia, the biggest challenge is the splitting of the water, as Joseph said, the electrolysis. You're right, that the energy efficiency there is quite bad. But there's other issues as well related to the intermittency of renewable energy and the fact that renewable energy is very distributed. But when you look on the ammonia synthesis side, it's as far as energy efficiency, electrolysis is a big one. If you look on the other side of the flip coin of using the ammonia, I would say the biggest challenge is particularly if we're talking about as a fuel, actually using the ammonia. So your research, Joseph, is obviously the decomposing it back into hydrogen. But as we often talk about, the other ways of using it are you can put it directly into an engine in a ammonia hydrogen blend directly into a combined cycle gas turbine, and it can generate energy that way just by burning it directly. Or you can also put ammonia into a special fuel cell. And those applications are, I think, some of the more challenging ones as far as seeing ammonia as a fuel, I think. What do you think?
Yeah, I would say the burning in a turbine has issues of NOx production, but you could also try to mitigate that with catalytic converters or with introducing steam to the mix. And in terms of the direct ammonia fuel cell, that's quite low in efficiency at the moment. But yeah, I would say that the biggest challenge at the moment is creating this clean hydrogen from water. If we look at the whole thing on the side of the ammonia decomposition, breaking down the ammonia, I would say that each one has its own, each possible way of getting the ammonia back, and energy back from the ammonia has its own particular challenges. Yeah. Okay, thank you. So Severine Miller is asking, how long will it be before ammonia is widely produced by renewable energy? Well, actually, widely produced, that's would require us to see into the future. But there are already there was a demonstration plant built in Oxford 2 years ago that demonstrates the storage of renewable energy, a wind turbine. There's also a plant being built in Australia, which would be doing this sort of green ammonia production, and one also in Saudi Arabia in the new Neom city. So we are getting the initial signs of this as being a way of ammonia being produced by renewable energy. In terms of widely produced, I would say maybe in like 10 to 15 years. What would you say, Colin?
Yeah, I mean, it's really hard to predict the future. What I would say, sort of related to this question, is that the economics of whether you make ammonia the conventional way using fossil fuels or from renewable energy, the economics there are actually very sensitive. So the example I always think of is back at my undergrad at University of Minnesota. They built a plant there to make ammonia from renewable energy, and that project was funded by farmers in Minnesota who wanted to know if they could make ammonia from wind energy on their farm. And the reason why they wanted to know that is because this was back in mid 2000s, 2005, 2008, something like that. And back then, natural gas prices were quite high. So the farmers looked at this and said, we can't keep on paying this price for ammonia, which was being made from natural gas. And they said, let's look at renewable energy. So since then, the natural gas prices plummeted, and now no one's really looking at it that closely, except for, as far as a clean sort of fuel option, not directly from the economic standpoint. But it just shows that the economics there are actually quite sensitive. You don't need gigantic increases in the price of natural gas for ammonia from renewable energy to start becoming possible economically.
Yeah. And if a country, for example, has abundant renewable energy but doesn't have any fossil fuel sources, then it might find that for its case, it's cheaper for it to try to go about producing the ammonia from its clean renewable energy, for example. So yeah, it depends on the price volatility, but also on what region of the world you're in. For example, there's a lot of attention from Australia in terms of making green ammonia. And other places that have abundant renewable energy. So those places will probably be faster in terms of getting there. All right, so Andrew Haddon's asking, what is the cost of ammonia compared with other fuels? So in terms of other conventional fuels at the moment, it's difficult because ammonia is not actually used as a fuel generally widely right now. So you can answer this in terms of like, what is the cost of fertilizer ammonia, or what is the possible cost? How would you go about this one, Colin?
I think we have to think about it in terms of hydrogen, as we usually do, because we really think about ammonia as the alternative or complementary even to hydrogen. So I think it's good to look at those costs. And there's a paper a white paper from the Royal Society that we know very well, that explains this very, very clearly, that in a lot of cases, if you're trying to move energy around in either hydrogen or ammonia, as you're sharing on the screen now, it's actually significantly cheaper to do it with ammonia in all cases relative to hydrogen. So cost of ammonia compared to other fuels, you're right. We can't really compare it with conventional petrol or natural gas, because it's not really, it's an apples and oranges comparison. But if we compare it with hydrogen, the cost is actually quite beneficial to use ammonia rather than hydrogen for these applications.
It's when we talk about large scale storage or long transport, then it becomes much easier to be moving around or storing a small volume of a liquid rather than hydrogen gas or super pressurized hydrogen cylinders. So yeah, it's a question of scale in that sense. So yeah, thank you for that question, Andrew. So Atharva is asking, do you think in the future we can rely completely on ammonia as a fuel source and stop using fossil fuels altogether? Well, in my opinion, I think that when there comes a point where it makes economic sense to not use any carbon fossil fuels anymore, or where policy pushes us to not use fossil fuels, then I think at that point we will have to turn to alternative ways of powering the planet. And ammonia, I think, will definitely be playing a large role there because it's our only way, essentially, to make our own fuel with the nitrogen, which is everywhere in the air, and the hydrogen, which we can get from water. And I think, as I was saying, in large scale, long distance transportation, ammonia will make the most economic sense. So I think in the future we can rely on completely using ammonia as a fuel source, but at the same time, it is not like a one glove fits all kind of thing. There's, for example, with cars, we see that batteries are make the most sense. The basket will have many eggs in it, so we will also be seeing other forms of fuels, maybe some biomass, nuclear energy, providing some power to us. Well, anything you would add, Colin?
No, I think that sums it up pretty well. All I would say is I don't know whether we will be able to completely transition away from fossil fuels 100%, because 100% is difficult to get to. But what I would say, and I think we would both agree on this, that the backbone for a renewable fuel economy is going to be ammonia. Now, like you said, it's not going to be that it's going to be applied everywhere, but it will be the backbone because it's so easy to transport and it's so dense in energy.
Indeed. All right. So Paul is asking, so is it better to burn ammonia directly or convert it back to hydrogen? What are the losses of hydrogen to ammonia, from hydrogen to ammonia to hydrogen? So that's a very interesting question, Paul. And at the current moment, I would say that it's better to convert ammonia to hydrogen first and then feed the hydrogen into a fuel cell or into a PEM fuel cell. And I would say that because I think the fuel cell technology is readily available. And the issue with burning it in a turbine is that you will be producing nitrogen oxides, which we don't want to be doing because of the acid rain issue there. So at the moment, I think it's better to convert it back into hydrogen and use it at point source, use the hydrogen at point source. And in terms of the overall losses, the round trip efficiency varies somewhere between 15 to 19% of the hydrogen to ammonia to hydrogen. Is that correct, Colin?
Yeah, it's something. It's around 20%. Of
Around
course, we're trying to improve that,
yeah.
but it's important to also say that that's relatively close to what it is for liquid hydrogen, or 700 bar hydrogen as well. So the efficiency isn't actually as bad compared to hydrogen as you would think it is.
Yeah. That's the overall round trip efficiency. The actual going to ammonia and back to hydrogen is not that big of an energy cost because it's outweighed by the benefits which you will have in terms of the storage and the transportation. Kartik's asking, do you think that the corrosive nature of ammonia may limit the widespread use of ammonia? Hydrogen seems like a safer alternative as a fuel. So, Colin, maybe you want to talk about the anything you also mentioned. There was a study once about the public perception of ammonia, which you saw once.
Yeah, so ammonia is corrosive. That's not actually usually the first thing people object to about ammonia. The first thing people usually object to about ammonia is that it's poisonous, technically. It can kill you at a few hundred ppm. The thing is, you can also smell it at around 1 ppm. We can attest to that personally in the lab. We can smell it at that low of a concentration. So it's actually pretty safe because you know if there's ammonia in the air, even at low levels that are much below what it would take to kill you. The corrosive nature of it, I mean, yes, that requires some equipment specifications. We deal with it every day in the lab, but it's already well known what those equipment specifications are and how to deal with them, because as we talked about, ammonia is transported all over the place already. So these equipment requirements to deal with this corrosive nature of it is already in place. In fact, you can transport it in a pipeline that's 1,200 kilometers long. There's a pipeline like that in the United States. So this equipment to be able to deal with that corrosive nature,
It's already there.
it already exists. And as far as hydrogen being a safer alternative as a fuel, yes, it's technically not poisonous, but you can't smell it. And once you know the hydrogen is there, because it's been ignited, that might be too late. So personally, I would feel safer with the tank of ammonia than with the tank of highly compressed hydrogen, but that's just me.
Yeah, it's a very interesting question. But yeah, in terms of the corrosive nature, as Colin is saying, the infrastructure already there. We send ammonia across very long pipelines. It's handled so widely, and I think the perception changes quite a bit depending on who you speak to. I think Colin, you mentioned once at a conference, the perception between rural people and city people is quite different. Rural
right.
people who work with ammonia all the time as fertilizer go like, yeah, what's wrong with that? Like,
right.
a fuel
So
which they know how to use and they know how to handle it.
yeah, so some people have done studies, as you're saying, people have done studies where if you look at the perceptions of ammonia for people who live in a city relative to people who are in rural environments, particularly farmers and that sort of agricultural background, there's a completely different way of viewing ammonia, that people in the cities tend to freak out about ammonia more, again, because of its poisonousness, which is true. But then when you talk to the people out in rural areas, they don't really freak out about it as much because they work with it every day and they know that there's these safety procedures in place. We know how to deal with ammonia. We know how to be safe when dealing with ammonia most of the time. There are exceptions. Accidents do happen, as they happen with every field. But we know people who are farmers, particularly in the United States, I know that they use ammonia directly, extensively, and they know how to deal with it and be safe about it. So
yeah. I mean, it's like having natural gas at home. Natural gas leak can be very dangerous as well. It is definitely, every fuel will have a risk associated with it. I do think though, because of the industrial familiarity with ammonia already as a fertilizer, I could really see it being used in very soon times in sort of a power station setting where it's under safe regulations and it's already very handled by farmers in many places. So yeah. Thank you for that question. Alex is asking, are there any risks associated with storing large amounts of ammonia? I think we pretty much answered that with the discussion of its corrosive nature and the toxic aspect of it. Andrew's asking, can you burn ammonia without producing oxides of nitrogen? That's a very good question. And Andrew, there is some research being done at the moment where if you blend in some steam into that mix and blend in some hydrogen as well, so if you, for example, use a catalyst to decompose a bit of the ammonia into hydrogen and then also introduce some steam, apparently there are ways where you can really reduce the NOx emissions by a promising amount. And in terms of extra removal with a catalytic converter, that's also possible. So there is research being done on how to burn ammonia in a way that doesn't produce NOx emissions. Absolutely. And then, John, is there another group in Cambridge researching metal hydrides for hydrogen storage? Not that I'm aware of in Cambridge. I'm not sure. Do you know of any, Colin?
I don't know of one for metal hydrides, but I know in our department, there's a group working on MOFs, metal organic frameworks for hydrogen storage. So there are other ways to store hydrogen with benefits and drawbacks as well.
Yeah. But it's all about, I guess, the general theme is that there's a lot of research going out there on how to go about creating new fuels or new ways of carrying or storing energy in chemical bonds, in our case, and also other forms, by whether storing the hydrogen in a metal hydride form or taking it into a metal organic framework. So these are all ways in which people are trying to tackle this solution of how do we replace carbon, how we move on from carbon, then how do we go about making our own fuels in a way, or making, and the other metal hydride or MOF, it would also be, I would imagine, hydrogen coming from water, in an electrolysis source. So going about creating new fuels of the future in a renewable way that doesn't involve carbon. Yeah. So I think, yeah, if there's any more questions, please type them in the chat. you said, it could be about anything, our daily work as scientists, etc., or related also to the topic we were discussing about energy and fuel. And yeah, let us know. We'll just wait for a few more minutes, see if there's any final questions, and then I think we will wrap it up. All right, let's see. Yeah, a lot of good questions. Colin and I are always, we were surprised last time on our talk on Tuesday at how specialized the questions are. We were thinking it would be a more younger audience who weren't so specialized. Usually at the science festivals in Cambridge, it's a lot of younger audience members. All right, I don't think there's any questions. What do you think, Colin? Should we wrap it up?
Yeah, we can wrap it up.
All right. Well, thank you all very much for your time. And we hope that you enjoyed the talk. And let us know if you have any other questions. You can always get in contact with us. I think we've shared our research group's website, so all of our contact details are there. And otherwise, thank you so much for your attention. And we hope you learned a little bit, you learned something new today. And yeah, have a lovely evening and a great bank holiday weekend. Bye. All right. Let's see what happens now.